Welcome everyone. So very happy to see everybody here at 9:30 in the morning for the 2023 Cryo-EM course. This is the schedule for the week, which I'm sure you're all aware of, and it's being hosted by myself and Giuseppe. I'll just remind you that we have done this course twice in the past, back in 2014, as you can see here, and all the lectures have been recorded. In 2017, in 2020, somehow we were all busy. I don't know what happened, but we're still on the correct cycle of every 3 years, excepting that one. So with that, Giuseppe's going to introduce our first talk.
Good morning, everyone, and thank you for coming at 9:30. Coffee will not be served after. So our first speaker is Richard Henderson, who will tell us about the influential publication in Cryo-EM. Please, Richard.
Thank you.
So we need to move this. Okay. Yeah, no, all this.
Please go.
Okay.
There's only one socket working. We'll wait to make sure it works. So.
Yeah. There we are. Thank you.
Good. All right. Well, it's a pleasure to be here speaking. I think there are lots of talks out there about EM and about what happened and how we got here and so on. And so, and all of them, a lot of them are available on YouTube, so you can still watch them. And obviously the history doesn't change. If you go back 10 years, what happened before that was the same 3 years ago or 6 years ago and so on. So I thought rather than revamping that and trying to bring it up to date, it'd be more interesting just to talk about some of the papers that have had a lot of impact or have been or were landmarks in a way. So I've got about 20 slides. Each one's got several references on it, and I'm just going to talk you through. And then if you think one of the references that you haven't read is interesting, then you have to go and read it again. So here is the first slide. So I thought I'd start in 1897. When the existence of electrons wasn't actually known. And J.J. Thomson down in the Cavendish lab here in Cambridge, he was the first one to integrate a lot of experiments he did with a cathode ray tube, which was like an oscilloscope with a beam of what we now call electrons, hitting a fluorescent screen. And then he was able to work out that these particles, which he called corpuscles. And he used that term even 9 years later when he had a Nobel Prize for that work. The actual term electron was invented or proposed earlier on by somebody, by an Irish scientist working in Dublin. But he worked out that the charge over mass ratio was many times less than that of a hydrogen atom, and so they knew that these particles were very small. He didn't get that it was 1,800 times smaller. He got maybe 700 or 800, but it was really a very big step forward. And you can read about it in his fairly short Nobel Prize lecture. And then that was how it stood, with lots of other work. It was actually a year or so after the discovery of X-rays by Röntgen, who used a similar tube, but looked at the X-rays that were produced when the electrons hit the phosphor. And then they would go through matter, and Röntgen had an X-ray of his wife's hand that gave the X-rays a kickstart over electrons. And then lots of things happened. Hans Busch was a German scientist who worked out from some geometry of magnetic field lines that you would be able to make a lens from axially symmetrical, cylindrically symmetrical magnetic field that would focus them in 1920. Not a lot of people know this paper, but I know Fritz Semlin that we worked with in Berlin. He was in the Ruska Institute. He said that this was very, very important. He's often forgotten. So this is an important paper. Of course, you have to translate it from German, but you can do it with Google Translate now. And then a bit later on, Ernst Ruska, who was had a more of an engineering background, used this information to develop the first electron microscope, and this is a paper with Max Knoll. They patented it, and Siemens was the first company to start making electron microscopes commercially around about 1940. And then carrying on from Busch and Ruska, Scherzer was the one who did more serious calculations about magnetic fields and showed that you couldn't, with magnetic lenses that were circularly symmetric, you couldn't ever get perfect lenses. You would always have aberrations like spherical and chromatic aberrations. And it was Scherzer's disciples that have gone on to develop some of these aberration corrections that we see now in some of the microscopes like CC, CS correction. And then Ernst Ruska's brother, Helmut Ruska, was more of a biologist and medically oriented. And he's the one who took, throughout 1940s, 1950s, electron microscope images like this one of bacteria and viruses. So, for example, T4 and so on. So that was the early beginnings. That was, let's say, up to 1950. Lots more papers, but none of them were very high resolution. And then in the 1950s, particularly people who are working in this lab or associated with this lab got involved developing staining methods that would give you higher resolution than some of these earlier methods. And Hugh Huxley with Zubai was one of the first. It wasn't published before this, but they were doing it before that, using negative stain, where you embed the particle in a puddle of stain and let it dry. And then what you get is an image where the dark area is where the particles aren't, and then you get a sort of plaster cast of the particle. So that was Huxley and Zubai, and then Sidney Brenner and Bob Horn, who was in Norwich at the time, have papers in using different specimens. So Huxley and Zubai did turnip yellow mosaic virus and other things, including ribosomes, and then Brenner and Horn had these TMB pictures. And then I thought I'd put also in this separate paper where they actually looked at adenovirus, because adenovirus is one of the samples that people have looked on over the years as the resolutions got better and better. Okay, so jumping now to the late 1960s, and I'll say a little bit about each of the, so in the development of all the methods that we have now, there were lots of people enthusiastic about it, and they were in different centers. So they each had their own culture. And the lab here was sort of dominated by Hugh Huxley and Aaron Klug, who were always very keen on electron microscopy. Actually, Aaron used to say that he found X-ray crystallography too boring, and therefore he wanted to work on electron microscopy. So Aaron and Hugh were the ones who pushed it, but they also had a group, and working with Aaron Klug was David de Rosier for about 3 or 4 years in the late 1960s. And the paper that's been a big landmark was this paper, de Rosier and Klug in Nature, where they took images like this of T4, phage tails, and then with the assumption that each image was a projection of the structure, but from different angles, used the helical symmetry to make this 3D model, and then generalized it to make a story about how the future of electron microscopy in three-dimensional structure determination came from similar work to this. But they also had other people in the group. So these images, for example, this one, were recorded actually by John Finch, who came with Aaron. John Finch had been a PhD student with Rosalind Franklin and came with Aaron when the lab started. And he was the one who did all the electron microscopy at the beginning, actually, apart from Hugh Huxley. And then Tony Crowther and Linda Amos joined them and expanded the work over these initial works. And then this one was in about spherical viruses with Tony Crowther, this bottom one, tomato bushy stunt virus. And then there was a meeting at the Royal Society, a whole volume with all the people who were involved from all over Europe and America who came and gave talks. So there is a Proc Roy Sock or Phil Trans Roy Sock proceedings from a meeting that Aaron and Hugh organized, which I've not cited here, but some of these papers come from that. And that really kick-started 3D EM as a method, but it was limited at that stage to looking at structures that had been preserved in a different way, particularly negative stain. And I think it was Aaron and his early collaborators like Berger and Finch and so on, who went to a lot of trouble to prove that these images were essentially projections through the entire thickness of the structure, whereas other people thought they were looking at the surface. And then they had all sorts of papers that's not cited here to try and justify that. But in the end, that became the established dogma. And then another work that came from the lab here was, I haven't put it in actually, but there's another paper by a German scientist called Thon, who showed that a lot of these images people were taking of carbon films or negatively stained structures, they had rings in the structure like this, which we now call Thon rings. And Aaron and John Finch, they always wondered where they came from. And Harold Eriksson was a postdoc with Aaron Klug, and he worked out from images like this of catalase with a certain amount of defocus that you could analyze the strengths of the diffraction spots from a crystal of catalase, which are the dotted lines here, and then fit them to a curve, which is what we now call the contrast transfer function curve. And it consists of a real and imaginary part. So from the phase shift of scattering of electrons, its pure phase contrast gives you this curve, but because it's negatively stained and they have a lot of heavy atoms in them, a proportion of the beam is actually scattered outside into the column or into the objective aperture. And so you get quite a large amount of what we call amplitude contrast, about 35% of the peak of phase contrast, whereas with unstained structures, it's much less here, maybe 5 or 10%. And then in work that Nigel and I did in 1975, where we were trying to move away from negatively staining the structures and analyzing the plaster cast, if you like, that the stain gave surrounding the structures, we moved over to trying to take pictures of unstained structures. Nigel was working on catalase crystals, and I was trying to work on these 2D crystals of purple membrane. And these were high-dose electron diffraction patterns and then low-dose diffraction patterns of the same area. At the high dose, the protein's crystallinity was destroyed, but at low dose, you could see these diffraction spots from the crystal lattice. And these are that's a plot of the intensities of these different diffraction spots as a function of radius, showing you that you have peaks and troughs, which are the Thon rings that you got earlier on with Eriksson and Klug. And then these are the two amplitudes from the high dose picture and then the theoretical fit to them. And then there's another paper by Dick Wade, who was working in Grenoble, who did a much more thorough and visually appealing explanation of contrast transfer functions, 1978, that's useful to do, and I haven't shown a picture of that. Okay, so that was a lot of the very early early papers. So then there were other centres in Europe. So, we're obviously here at MRC in Cambridge. We know about the Cavendish, we know about LMB, but out there in Europe and America and Japan, there were lots of other groups. And actually, the reason that we're in such a good state at the moment is because all of these different people thinking in different ways were contributing to the development of the field. So I thought it'd be useful just to put in one or two slides about. So Walter Hoppy was the founder of what you could call now the Martins-Reed Electron Cryomicroscopy Center there, which is, where Baumeister and other people now are working. But he was originally a small molecule X-ray crystallographer, and actually came here to the lab in the 50s to learn about protein X-ray crystallography. And then a bit later on, switched his efforts and his interest over to electron microscopy. using electron microscopy as a phase determining diffractometer. So he was trying to draw the parallel all the time between electrons and X-rays, and he was very good at that. And his colleagues, Gassman and Hoppy, were very dominant in the 60s, and his students were people like Joachim Frank and Michael Rademacher, and here are a few of the papers out of them. So you can see Joachim Frank's, probably more or less his first paper, involves computer analysis of electron microscope images, and then he carried on with spider and then ribosomes and lots of other things after that. And then one of the other people working with Walter Hoppy was Hegel, and they published 2 or 3 papers back to 1970 and coined the term tychography, which we don't use yet or not very much in biology. There is a paper from Dave Stewart and Angus Kirkland recently using it on frozen hydrogen pictures of big viruses. But it has potential for being useful in the future, and some of certainly people in material science use this as a way of going beyond, because it's essentially a diffraction, it's a coherent diffraction method. But Hegel and Hoppy are the ones who started it and coined that term. And then Hoppy wrote dozens and dozens of papers, and one of this one was a series of 3, where his enthusiasm was towards essentially electron tomography, where you took individual objects. In that case, they were negatively stained, either ribosomes or fatty acid synthetase. And there was a group in Munich, Theodor Lunen, who worked on fatty acid synthetase. So they had these 2 big objects, ribosomes and fatty acid synthetase, which people still work on nowadays. And the idea was that they would negatively stain them and take pictures from different angles and do essentially early tomography in the electron microscope. And they had these 3 papers sort of almost back to back in one of the German journals in the 1970s. And then this is a review. And then in 1982, when the Nobel Foundation awarded Aaron a Nobel Prize, Hoppy was not entirely pleased by this. So he wrote this long review explaining all his views and so on. And he always used to say, of course, we did this 20 or 30 years earlier. And it was true. It's just that he never translated it into reality. He was a very clever theoretician. So that the Munich Martensried, the Max Planck Institute, Structural Biology 1 and Structural Biology 2, it's still very strong there. And it all derived from Hoppy and the people who were PhD students in his group. And then another group was where Marin Van Hill was trained in Groningen. Ernie van Bruggen, he was more in sort of biology oriented, but people like Marin Van Hill, Egbert Boekema, and Bettina Boccia all came from Groningen, and their interests were focused on another specimen in the early stages, hemocyanin, earthworm hemocyanins, and other molecules. And these are still worked on actually by Marin Van Hill. It's a tradition. So if there was a favorite specimen in Groningen, there were lots of them, and it spread out into X-ray crystallography. So Wim Hol also did lots of work on hemocyanins using X-ray crystallography. But you can also see that when he was a PhD student in Groningen, he did some collaborations with Joachim Frank. This was Van Hill and Frank and Van Hill, and they started one of the earliest ways of doing classification of particles. So the idea was you would align the images of all your particles and then put it into a mathematical matrix inversion method, which they called multivariate statistics or correspondence analysis. And now we call it just 2D and 3D classification, because it turns out the way they did it wasn't the important thing. It was the fact that they were doing this classification. And for many years, both Imagic, that was Marin Van Hill's initiative, and Spider from Joachim Frank, they were the dominant softwares in the analysis of single particle images. so that came from Martinsried and from Groningen as sort of the incubator for that sort of work. Okay, then another one was in Europe. Another center for electron microscopy was in the Biot-Centrum in Basel. The Biot-Centrum was opened in 1970 or so, and the leader there was Edward Kelenberger, who had a lot of students, including Jacques Dubbo, Uli Eby, Andreas Engel, and other people, Ross Smith, and so on. And these are some of the papers that they published. And they're not well known either, partly because they were sort of journals that sort of changed their name, so they weren't so popular. So they were very keen on publishing in this journal called Experientia and the Journal of Ultrastructure Research. And these are now, this metamorphosed into the Journal of Structural Biology when Bob Glazer became the editor about 25 years ago. And then Experientia changed into cellular and molecular life sciences. So we've sort of lost that connection. But you can see that the enthusiasm for Kelenberger was in scanning transmission electron microscopy, where you have instead of having an image and you have coherent phase contrast imaging, you scan the beam over it and then look at the scattered electrons, energy loss ones, non-energy loss, near axis, far from axis. And there are lots of different modes of imaging, and they were very enthusiastic about that. So they were looking at different specimens using what they call dark field electron microscopy and STEM imaging, and looked at a variety of structures. Kelenberger was in Switzerland. There was a big focus on looking at bacteriophages. So the biology side of their work, apart from cell walls and so on, were bacteriophage T4 and T2. And for example, people like Uli Lumley, who developed Lumley gels on the phage, he was working with Kelenberger on these same phages as part of that Swiss effort to develop early structural biology. And they had STEM projects. And eventually, of course, Kelenberger retired, but the people who'd worked with him, for example, Andreas Engel, they went to EMBL, and there was a big project encouraged by John Kendrew, who was the director then, to develop scanning transmission electron microscopy at EMBL with a liquid helium stage. And they worked for about 10 years or something like that with Arthur Jones. That was a kind of follow-on from the Kelenberger's work. And then that was, of course, how Jacques Dubbo got going. He was recruited then, along with Andreas Engel, from the lab in Basel to EMBL when it was decided that EMBL should make a big investment in electron microscopy and electron cryomicroscopy. Okay, then moving on, another major lab with an interest in determining structures in biology came from Bob Glazer's work. And Bob Glazer was a young assistant professor at Berkeley in 1970s. And one of his important papers here was when they did this top left picture, looked at the electron dose of room temperature samples of little crystals of adenosine or valine, an amino acid or a part of a nucleic acid, and looked at the diffraction spots as they faded and showed that at room temperature, this T1/2, if you like, for amino acids, about 1 electron per square angstrom. That's the maximum dose, and then it was destroyed, whereas adenine lasted a bit longer, and that's still the case in structures like the ribosome or the aromatic structures are more radiation resistant than the aliphatic ones. And so that's carried over into current technology. But that paper was the original one. And in it, Bob also said that if you calculated the amount of information you get in the image at doses like this, there wasn't enough to determine structures. So you needed to do averaging of hundreds or thousands of molecules before you could get the structure. So that was an early indication of the fact that you're stuck with the properties of electrons and radiation damage, and you couldn't do any better. But Bob also had a number of students. For example, Ken Taylor was probably one of the first, and Ken Taylor had these two papers in Science and Journal of Ultrastructure Research in the 70s, where they tried to overcome this problem of radiation damage at room temperature by cooling the crystals. But the vacuum in the microscopes then weren't good enough to get down to liquid nitrogen temperature. They weren't good enough to produce properly amorphous ice. Didn't come till later. They could only get to about minus 100. But nevertheless, they showed that these electron diffraction patterns of initially catalase crystals faded several times slower when you cooled them. So that was the beginning of, let's say, cryomicroscopy, electron cryomicroscopy that we now use all the time. And of course, in parallel with that, some of the X-ray crystallographers, Michael Rossmann, Robert Huber, and so on, they were also trying to cool crystals to overcome radiation damage with X-ray crystallography. So there was a sort of parallel thing, but none of them could get very cold until the mid-80s, until the vacuums got better and so on. And then also, I thought I'd mention this again, we did do electron diffraction also at room temperature, and also found that something like 0.5 to 1 electron per square angstrom for protein crystals was a similar spot fading thing. So coming now to another topic that has great potential in the future, although hasn't really caught on properly yet, and that is we all have the defocus bright field phase contrast as a way of getting contrast in images of unstained molecules in ice or just dried. So there's always been a very great interest in having the equivalent of the Zernike faceplate in optical microscopy. And Nigel had a lot more papers than this actually in the 1970s. And Nigel was persuaded by Hugh Huxley to come from material science downtown in Cambridge, the material science department, to come to the lab and work on, try and work on biological structures. And Nigel's early idea was to make a faceplate with this objective aperture with a hole in it, with a thin wire across it, which he made with spider web coated with gold. And the idea was the direct beam in the back focal plane of the microscope would hit the wire, charge up, and the electric field from the charging on that wire would cause a phase shift in the direct beam and the beam near the direct beam, but no phase shift further. And then he was able to get 90-degree phase shift with difficulty, and that was one of his nicest images of TMV and T4 phage with a negative stain, but with a faceplate, so that you get really nice, good contrast at very low resolution. And so all these are really nice papers, stacked discs, and so on. And then more recently, Radiston Danev, who had worked in Japan for many years on other types of faceplates, which had a hole here and then a carbon film that caused the phase shift in the diffracted beams, found almost by chance really that if you just put the beam through a continuous carbon film, you don't bother with the wire or the empty space, that where the beam was would get charged up and cause a phase shift as well. And this was they called the Volta faceplate, and that's been introduced both by Thermo Fisher and by Jayol. And here is a diagram with a nice picture of a proteasome with contrast right down to low resolution. But the phase shift, you can see here, as you record different images over time, the phase shift goes from not zero, but 30, 40 degrees up to 90 is what you want to get the Zernike phase shift contrast, up to higher, and then you move to a different part of the continuous carbon film and it drops again. And for a while, this was very popular because you could see what you were doing, but it turned out that the inhomogeneities in that charge distribution of the continuous carbon film meant that it it ruined the really high resolution parts of the images, and so it was abandoned. And people just, once they realized that the specimens were good, they could just do bright field phase contrast. But we still need a really good faceplate that isn't quite as tricky to use as the one Nigel developed, and doesn't have some of the problems here. So that's not been solved yet, but people are very enthusiastic about the development by Holger Muller's group in Berkeley of the a laser pontomotive retardation faceplate. But that's still some way off in the future. But in principle, you might be able to get images like this every time without having to worry too much about it. Okay, so next is field emission guns, and certainly throughout the early 1970s and 80s, I think most people were using a tungsten filament as the electron source. But Albert Crew in the late 60s and early 70s had a vision for trying to get atomic resolution and look at single atoms. And alongside this, the contrast mechanisms, his idea was that you would get a very sharp, bright focus, a field emission tip, and rather than using that to produce a coherent, broad, bright field image, you would use the lenses to focus it on the specimen and then scan the beam. And this was scanning transmission electron microscopy, a bit like Kelenberger and Z contrast and so on and so on. And he was very enthusiastic about that, wrote lots of reviews that are very worthwhile reading. Other people joined him. This was Kelenberger and Michael Beer and so on. And then his group, John Langmore, Joe Wall, and Isaacson, tried their very best. But in the end, what happened was that the electron microscope manufacturers, have we lost something or other? Fine, just ignore it, yeah. The electron microscope manufacturers just developed an electronic way of switching from TEM to STEM, and Albert Crew's initiative gradually died out, and he was very disappointed about that. And then in the bright field defocus phase contrast that became the dominant method in structural biology, very few of the early electron microscopes had field emission guns, although Bob Glazer had one at Berkeley in 1980 or so, a gel 100B with a field emission gun that worked really well, actually, and we collaborated and used that at that time. But then the enthusiasm moved away from tungsten filaments and lower voltage towards higher voltage with a field emission gun, and the manufacturers weren't manufacturing them, and that was because we were worried about, at that stage, charging and coherence and so on. But eventually, Hitachi, Gel, and Philips all introduced field emission guns in the early to mid 1990s. Hitachi were first, and in the lab here, we did buy a Hitachi HF 2000, and we were one of the first labs to have a higher voltage microscope with the field emission gun, which gave you coherence and could get you to higher resolution. So that was an important stepping stone, but there were other problems. So it meant that you didn't get all the way towards atomic resolution easily every time, simply by having the field emission guns. So there were other things that were important, and one of them was aligning the microscope. And Fritz Zemlin, who was in Berlin in a Max Planck Institute, the Ruska Institute, which was the core of a lot of electron microscopy developments in lenses and aberrations and so on in the 70s and 80s. Fritz worked together with his colleagues, Kunas, Schiski, Herman, and so on, and realized that in the alignment of microscopes, let's say in 1980 or so, there were two methods of alignment. One is you would do your very best to get all the lenses lined up in a row. They were mechanically moved. And then you would either put a wobble voltage on the high tension itself. So that would be what they called the voltage center. And that was changing the voltage, and then the beam made its way all through the microscope, and you tried to align the beam to go through the specimen so that the image rotated. And that was an alignment that was addressing the entire beam path through the microscope. And the other method of alignment was to put a wobble on the objective lens current. And again, you get a rotation. It was a different rotation center because the beam never went straight down. It always wiggled its way down the column. And what Fritz realized in 1978, 1979 was that if you did the alignment of the column with the voltage center or the objective lens current center, the beam still was going through the specimen at an angle. It wasn't actually going vertical. You thought it was, and you adjusted the astigmatism to make it look beautiful, but it wasn't true. And so that was one of the problems we had in the early days with purple membrane. We couldn't get any of it. We see the spots, but the phases didn't agree. And there was this paper by David Smith, who was in Cambridge, who read Semlin's papers and wrote another paper called How Important It Is, Otherwise Your Images Are Uninterpretable. And then Fritz proposed a practical procedure, which was called the Semlin tableau. So here on the left, top left, is an image, is a diffraction pattern, computed diffraction pattern of an image. In the middle is a sort of near focus one with the astigmatism corrected. And then you tilt the beam by, say, 10 milliradians one way, and you're putting the beam in a specifically non-parallel position, and you get a perturbation of the pattern. You go the other way, and you should get the inverse of that, but you don't. You see, you go up here, and you go down. So that shows you that this central image does not have the beam going vertically. But when you do the procedure, which is that you change the angle of the beam in X and Y until the Semlin tableau gives you symmetrical images, plus and minus Y, plus and minus X, 45 degree. So this is an unaligned microscope, which everybody thought was aligned, but actually doesn't give you good true images beyond about 5 or 6. This doesn't go beyond 5. You get an image, but the features are wrong beyond about 5 or 6 angstroms. But after you've done what they now call coma-free alignment, you can get it out to, limited by other factors, 2 or 3 angstroms. So this is a big step forward. And then, of course, this is now built into microscopes, and now the microscopes are made better, and without doing this, you don't get as much beam tilt error as they got. This would be maybe 2 or 3 milliradians of beam tilt error that was being corrected by counteracting it. Now it's probably only 0.3 or 0.4 milliradians, but still important. But this is a recent paper from a group in Japan who have been developing in parallel different types of aberration corrector. And you can now see that the Semlin tableau is really beautiful now. So here is a perfectly aligned beam with no beam tilt, and you go out here and you can see they're all nicely symmetrical. And then because this microscope also had a CC and a CS corrector, if you switch it on and do the alignment, you can see the Semlin tableau gives you nice pictures in all these different directions. So anyway, we do this. It's now almost invisible to the user, but it was a very important thing. And actually, Fritz created his own internet address and his own postage stamp with the Semlin tableaus on it. So that was a good one. Okay, so then we come to Jacques Dubbo's work after he went from Basel with Kelenberger in 1978 to EMBL, recruited by John Kendrew to investigate high-resolution EM and the behavior of ice and how to preserve specimens. And he worked from 1978 to maybe 1982 or so, looking at the behavior of water. And this is his famous picture, really, which is electron diffraction patterns of different types of frozen water that were prepared in the electron microscope. So if you just take a thin film of water and cool it down slowly, it crystallizes, nucleates about minus 40 and so on, and you get hexagonal ice, which has big crystals. And when you take an image of it, you get these what are called bend contours because the ice isn't completely flat, and you do the electron diffraction pattern, and you get diffraction spots of hexagonal ice, which is what you get in snowdrops or on a pond in winter and so on. That's the typical ice. And then if you freeze the thin film of ice fast enough, and Jacques developed this with Mark Adrian and let's see, we've got Alistair McDowell and Mark Adrian were the two main people who were involved in developing that. You blot your thin film of ice, plunge it into liquid ethane near the temperature of liquid nitrogen, and you get this amorphous ice here. It's got obviously some contamination on it, but its diffraction pattern is continuous with no spots, just a broad band at about 3.7 angstrom resolution. And then if you warm that, let's say between minus 100 and minus 140, it changes at a different stage. You get converting that amorphous ice into cubic ice. And they had a lot of papers. They're well worth reading, actually. So Journal of Microscopy and Journal of Physical Chemistry, these two papers, 1982 and 1984, are investigations of the behavior of water at different temperatures. And then, of course, there's even more interesting behavior when you go below liquid nitrogen temperature down to liquid helium temperature, which problems that are not really quite solved. And we had a talk from Josh Dickerson and Chris Russo's group recently about a lot about. So there's still a lot of debate about what happens below that. But these papers, and then eventually his review in Quarterly Reviews of Biophysics 1988 summarizes a lot of things and gives lots of very good pictures. So this one and the references in it are essentially the beginning of electron cryomicroscopy of single particles, viruses, bacteria, muscle filaments, and so on. So that was, and actually, in the 1980s, EMBO used to run training courses, lecture courses, and practical courses. And at that stage, I was on the EMBO course committee where you had to suggest different topics. And of course, we knew about this, and we said, well, this would be a good course to have. And Jacques agreed and ran a course around about 1984, 1985 in how to do this, how to make these thin films of amorphous ice. And Linda Amos and I had a student called Guy Vigers. We thought, oh, it would be very good if he'd done about a year of work with us, working on tubulin macrocycles. We sent him to Jacques' course, and when he came back, he said, this is so exciting, and he resigned from our PhD project and then switched to working with Tony Crowther and Barbara Pierce. And that was and Guy's work, so his second year as a PhD student, as a result of going to the Cryo-EM course where Jacques was essentially training people in what people realized was going to be a very important breakthrough. Guy's work here, Guy Vigers with Tony Crowther and Barbara Pierce, the first three cryo-EM 3D structures ever determined from these thin films of particles frozen in amorphous ice were these top three here. So the first one was Jean Le Paul, who was working in Jacques Dubbo's group, and he took the same T4 phage tails that David de Rosier and Aaron had worked on with negative stain, and put them in ice and got this structure here. And they didn't have very good 3D rendering programs in those days. You saw the David de Rosier ones with balsa wood, and this is still not very good. Whereas Guy Vigers, one of the programs he wrote was a program for doing this nice rendering. So they got a much nicer looking picture but it's 45 angstrom resolution structure. Both of these are like that. And then Jacques himself worked with two mathematicians at EMBL to work out the structure of an icosahedral virus, a Leaky Forest virus from EMs. And these were the three structures, 1985, 1986. The first three done by Cryo-EM, and with just not much background, not much computing power. And then I thought I'd put this one in as well. This was one of the first papers published by Dubbo here was cryo-electron microscopy of viruses in Nature in 1984, where they took pictures of adenovirus, and this is part of one of the pictures was on the front cover of the Nature in 1984. But it took them from 1984 to 1991, 6 or 7 years, to go from the 2D images to the 3D structure, because the software wasn't very well developed. And that was Phoebe Stewart working in Steve Fuller's group at EMBL alongside Dubbo, who wasn't so, he developed, his interest moved on to thin sections and tomography more than that. Okay, and then the first time that single particle EM got below 10 angstroms came from work that Bettina Botcher did here. And remember, Bettina came originally from Groningen with Ernie van Bruggen, but she came here as a postdoc to try and get higher resolution and try to work on TMV and so on, and worked with Tony Crowther, and they had this specimen, hepatitis B virus cores, that came from Nikolai Kisilev and Paul Pumpens, who were in Latvia or Moscow and so on. They brought the sample, and this was a mixture of T equals 3 and T equals 4 states. This was done on film, but on a microscope without a field emission gun, and they got to 30 angstrom resolution, published it in Cell, and then Bettina went on, and then by 1997, so between 1994 and 1997, we acquired this Hitachi HF2000 with a field emission gun, and that made a big difference. So here was a similar image of a better sample that had been Sam Wynne developed by mutagenesis, one that was mainly T equals 4, so it's mainly T equals 4. And so with about 30 micrographs, got this 7.4 angstrom resolution structure that was published alongside James Conway's structure, which was a 9 angstrom structure of the same hepatitis B virus particles. And the Conway structure consisted of 1 micrograph or 1 field of view with defocus at 2 different values, a high and a low defocus, to give you a 9 angstrom structure of the same. And then it turned out that Bettina and Tony's structure was correct and higher resolution, but the wrong hand, whereas this one was lower resolution, but the right hand, just slightly interesting. And then, of course, they went on, and the most recent structure that I know of is Hong Cho's group at UCLA have done it again now, but they did it before these new detectors came in, and you'll hear about them from Greg. This was on, instead of 20 or 30 images, they had about 1,000 images on film, but then on a Krios with high voltage and a better field emission gun and so on. Okay, still there's a few more. E-volt sphere curvature was something everybody worried about. And at one stage, in a conversation with Bob Glazer, we said, well, we really need some less expensive microscopes so that the field can flourish. And so we were thinking maybe lower voltage would be good. And Bob said, no, well, actually, he'd prefer a higher voltage microscope because the E-volt sphere would be flatter, and then you wouldn't have to worry about the high resolution being lost. But then there were a series of papers, starting with one by David de Rosier in ultramicroscopy in the year 2000, where he was worrying about the beam coming into the specimen, the 2 beams being diffracted from roughly the same Fourier components. How could you, in the image that's formed from the 2 beams reflecting off almost the same but slightly different angles, you can see this is coming out at, say, let's say plus 0.1 degree and minus 0.1 degree. They're reflecting off slightly different Fourier components in the structure. And David had a couple of mathematical procedures involving 2 images that he advocated could be used to extract the information that had been lost by the overlap of these Fourier components of the image. But it was a theoretical paper and never really became of practical value. But then a few years later, he worked together with Niko Grigoriev, Matthias Wolf, who's now in Okinawa in Japan, and they worked out a practical method for implementing something similar to David de Rosier's by essentially doing single sideband motions to correct the images and extract both of these diffractive patterns separately. And Nico implemented it in his program FreeAlign, but they could never get it to work. And he was always worried that they'd done a programming error, but basically it was working. It's just that the images weren't at high enough resolution for big enough particles for it to make a big difference. Because in the eVolt sphere construction, with the diffracted beams coming out at these angles, you're sampling, instead of the value of the Fourier components in a plane, which you get for very short wavelength, very high energy electrons, you're measuring the amplitudes and phases of the Fourier components at a distance of delta z above the plane. So the difference between the right hand and the left hand Fourier component is 2. So when that delta z gets significantly big compared to the 1 over the size of your particle, then you get a mixture that you can't easily resolve. But it turned out that his modification of the program did work, and it took until about 3 or 4 years ago before the images and the structures were good enough to resolve it. And then in passing, Chris and I got involved with imaging of gold particles in ice, where you could actually see the fringes, they were so strong, and developed a slightly more sophisticated procedure involving masking it out as well. And Shores has implemented that in Relion 3 in 2018. So now you can get it either in FreeAlign or in Relion. You just say yes or no, you want it, and then it happens as if by magic. Okay, so still 2 or 3 more slides. I asked Nigel and Tony whether there were any other important papers that should be mentioned in a sort of overview of development of it. And for many, many years, say 60s, 70s, 80s, quite a large number of people were keen on going to higher and higher voltage. I think they hadn't solved the eVolt sphere image correction program that you can do in a computer. They wanted penetration through thick specimens. So there were initiatives here in Cambridge with Coslet and Owen Saxton. It was originally proposed to be a 1 MeV microscope. It was built down in Free School Lane. I think they still have bits of it there. They didn't ever reach 1 MeV. They reached 750, and then actually, by the time I saw it about 30, 40 years ago, it was only working at 600 kV. But these big projects take so long to build that by the time they've been overtaken often by other events. However, there was a big effort in Toulouse, which is still there, high voltage electron microscopy, and in Osaka. So these are some pictures of these. These are massive things. It cost hundreds of millions of pounds. And the 2 that were in Osaka, 3 MeV Hitachi and 1 MeV gel. I think this one is the Hitachi, and this one is the gel. The recent earthquake inactivated both of them, and it cost another 100 million to get them back up and running. But there are enthusiasms there, and there are possibilities, particularly for thin specimens and for STEM, that are worth keeping in mind for the future. And then 2 more little areas. I thought I'd mention electron crystallography. This was something that was how I got into electron microscopy, coming from X-ray crystallography. And initially we thought 2D crystals were the way to go, but it turned out they're just as difficult to make really good 2D crystals as 3D crystals. So we switched probably 20 or 30 years ago from 2D crystals to single particles. But these were the 3 earliest structures. That was bacteriodopsin, light harvesting complex 2 from Werner Kuhlbrandt's work with Daneng Wong and Fujiyoshi at EMBL and in Japan. And then Eva Nagala's working with Ken Downing in Bob Glazer's area of interest got alpha beta tubulin long before it was done by any other method. So these were 3, and there are now probably about a dozen atomic models made from 2D crystals, but it's been eclipsed certainly by the power of the and then the other type of specimen are these helical and filament images, muscle, or particularly in Alzheimer's and Parkinson's disease. I thought I'd just put these up as a sort of marker. Tony worked in, so let's say, 1980s to 1990 with initially negatively stained, this was slightly before cryo, and got images of these perihelical and straight filaments at about 20 or 30 angstrom resolution with stain. And then with John Berryman, they then showed that you could make some of them artificially. There's obviously a little flicker here from something, a dead fly in the projector. And then Anthony Fitzpatrick with Shaw's was the first time they were able to, I haven't shown it, but in the axis of these filaments, they are beta amyloid repeats, so they have a repeated, I think it's 4.8 angstroms or something like that, along the axis. But until this paper, no one was able to correlate that axial layer line with the equatorial layer line. And once you got that, you were into atomic resolution structures where you could see the side chains and interpret it. And then this recent work, lots of papers, but Sophia Lovestam's paper where they had lots and lots of them with different types of aggregation show that this particular type of geometrical filament is now really done really well. So I think I've got two more slides, and I'm not going to talk about them, but I thought you'll be having talks about hardware, about detectors, about tomography and so on, but I thought I couldn't have a historical summary without mentioning a little bit about the tomography side, which is largely a spin-out from Hoppy's original interest in it. One paper is Ohad Madalia in Baumeister's lab. Baumeister was the successor to Hoppy. In 2002 in Science, showing that you could get tomograms of thin sections of rapidly frozen specimens, and these were the actin and the ribosomes in that paper, dictyostelium slice, and then about 15 years later from Yulia Mohammed's work, again in the same group. Julia is now at EMBL, a much better micrograph of HeLa cells, in which you see the actin, now you have tubular, the ribosomes, you now have individual orientations of them with large and small nuclear pores and so on. So you'll be hearing about that later on. So that's my choice of slides. Obviously, they're all on the references are there. You can go and read them afterwards. So hopefully that's been a reasonably good overview and introduction. So thank you.